Hello, I'm Joshua Shearer, and I'm currently a mechanical engineering student at good old Purdue University in West Lafayette, Indiana. And I'm going to talk to you about free body diagrams and the law governing the motion of objects. First, we'll start with our free body diagram. A free body diagram is just a visual of an object and all the forces that are acting on it. So we'll start with our stationary box with a mass m, and we'll write in our coordinate system here, x being in the horizontal and y being in the vertical. The coordinate system is just a way of showing how the object is oriented in space. The law governing motion is known as Newton's second law of motion. The sum of all forces is equal to mass times acceleration, where both forces and acceleration are vectors. A vector just means something that has both magnitude and direction. So if we look over here, this force here has a magnitude. We'll say it equals 10 newtons. The direction is along the length of this arrow. So this force vector has both a magnitude and a direction. Going back to our box, we'll draw in a force. In order for an object to accelerate, there must be an on-balance of forces, meaning that all of the forces that act on the object sum to something other than zero. It's important to note that an object can still move even when the forces sum to zero, but that motion must already be in place before we sum our forces. So when we go to observe how this box will react to these forces, we'll go over here and say force 1 is equal to 20 newtons, and force 2 is equal to 10 newtons. When we sum our forces, we'll say rightward positive, force 1 minus force 2, because it's in the negative direction, positive being right, negative being left. Force 1 minus force 2 is equal to the mass of the object, m, times the acceleration of the object. We'll say the mass over here is 10 kilograms. We'll go ahead and write in our values here. We'll say 20 newtons minus 10 newtons is equal to 10 kilograms times the acceleration value. When we manipulate this algebraically, we'll get 20 minus 10 over 10, which turns out to be 1. And the units for this will be meters per second squared. We get meters per second squared because a newton is equal to a kilogram times meters per second squared. When we take force and divide it by kilogram, we just end up with acceleration equaling meter per second squared. It's important to notice that this is mass and not weight. Weight and mass are very different. Weight is equal to the mass times the acceleration due to gravity. This acceleration due to gravity can change depending on what planet you're on. So if you're on the moon or Jupiter or some other planet, this value will change than if you're on Earth, making your weight ultimately different. But in every case, mass is always the same, whether you're on the moon or any other body. So, there's our answer. Tune in next time for other interesting physics things.